All right, so I'm Dave Bonney. I work at Los Alamos National Lab. This is kind of an extension Gary referenced earlier this week in his talk about the infrastructure at Los Alamos and the new storage directions we're going towards, and they already have in production also as well. So this is an extension of that, and hopefully we can deep dive a little bit more into the details. Just before I start going at all, so anyone in the room, raise your hand if you've heard of MarFS before and know anything about it? Okay, wow, okay, it's more hands than I expected. Marchive, hands? Probably 1, 2, and GUFI. Other than the big show tent display earlier this week from Gary, did anyone hear the term GUFI before that? Okay, so at least 2. All right, so I'm just going to dive into this. Why are we doing this? What is it? How did we get here? How are we trying to move forward with storage? I'm not going to say cold, but in the colder tiers at LANL, underneath our big high-performance parallel file systems and burst buffers. So as Gary alluded to earlier this week, we're a simulation HPC site. We do weapons simulation, physics simulation on our big machines. One of the outliers in the way that we run our HPC site is that typically we have large jobs that run for 3 months to 6 months at a time. They use anywhere between 30 to 80% of the system memory just for that one job. The machine is essentially wholly dedicated to running that job as fast as possible, and we do defensive checkpointing to make sure that when things break, we can roll back a couple hours or so at worst. And as we do these, the checkpointing is both end-to-one and end-to-end. So we have this wide disparity in data storage sizes. So an end-to-one checkpoint is all the processors in the machine all hit a barrier. They say, okay, it's time to checkpoint because the system MTTI is 4 hours and it's been 4 hours-ish. So they dump all of their fields that they have in memory that they need to be able to restart down into a single file. And this is strided, it runs pretty fast. And then we also, but those are 80% of the system memory potentially. So you're talking about a 2 petabyte machine, that's a petabyte and change of storage in one singular file. The complete opposite end of that is end-to-end workloads where every single processor on the machine has its own memory space and dumps it to its own individual file. So it's a lot easier in the parallel file system. It's not quite as easy for restarting at different job sizes, but it also, when you're talking about millions of cores, you're talking about millions of files whenever this happens. So we have this extreme difference between petabyte scale files and gigabyte maybe-ish size files at the other end. So there's a huge disparity in the workload. So this is kind of a snapshot of what our system environment looks like as of, well, a little bit ago. We've got more machines coming in and things leaving. I'm going to be focusing mostly on the campaign storage part of this, which we started this 3 years ago, roughly, after a failed attempt at building a cheap, large storage system. So the campaign storage tier, for us, it's called campaigns, so it lines up with computing campaigns. But the campaign storage tier started as a drive to build a really cheap, big storage system. And one of the things we learned was you can't just take a big parallel file system and put cheap crap underneath it. Because the first thing we tried to build was a campaign storage system. It was about 2 petabytes of consumer disk with standard grade controllers, and then we're using the Linux SCSI or fiber channel exports from that to build a GPFS file system out of it. And one of the things we learned pretty quickly was, one, consumer hard drives aren't great when you put them in big RAID arrays. It should be obvious in hindsight. But 2, being able to recover from things when they go wrong is pretty critical to a big long-term storage system. And one of the follies we had for the original thing that we built with GPFS and these, Linux fiber channel targets over there that were exported in a kind of a not stable way, was that when something went wrong, it was really hard to figure out what went wrong, how it went wrong, how to fix it, especially as we started having a lot of disk fallout. Consumer hard drives, when you run on them for 2 weeks straight, 24/7, flat out, with something like a parallel file system pointed at them, they tend to not behave very well. They start to time out, your RAID arrays start to fall apart. Then you're just swapping out disks so quickly that all you're doing is rebuild, which puts more stress on them, and that's kind of ends up in a bad place. We didn't lose all of our data, but we did lose some of it, and that was an interesting couple weeks while we tried to clean up the mess when the whole thing fell over flat and the GPFS metadata was corrupted and the data storage was corrupted, and we're trying to figure out what was going wrong. It was not a fun couple weeks of my life. So we set out to build something that would fill that purpose. It's taking these big checkpoint dumps. We don't want to push them down to tape because tape is hard to parallelize. I shouldn't say hard. It's hard to parallelize for large single files in a safe way. I mean, you can certainly stripe really wide, but if you want to buy $150,000 in tape drives just to store a file that you might not be able to get back because it's across 100 tapes, it's hard to justify buying things like that, and it's even harder to keep them running. So, yeah. So maybe it's not obvious in this chart here, but this is not one namespace. We have not gone down the route of doing HSMs to have have the system move data up and down, in and out of tiers. One of the things that's pretty hard with science like this is that it's very human-driven. So as these scientists are building and running these simulations on the system, they may just see something interesting in the simulation output and say, oh, well, we have to do this other thing. And tiering up and down petabyte scale data sets is not something that you want an HSM to rely on, especially if you're only going to read it once, and especially if it reads up the wrong one, because because of, you touched the header and it said, oh, we're going to tier that whole entire petabyte up. Not only do you waste time, but you waste other users' time on the system as well, because they've got a reservation on the system and to be able to run their jobs. So these are multiple different namespaces. We're talking about campaign storage as a separate namespace. The shared scratches are a separate namespace. The home and projects are a separate namespace. The archives is a separate namespace. It's all human-driven up, down, through the stack. Anyway, just went over all that. So why did we make this worse by adding more tiers? Trinity came in, we added a burst buffer. There's a lot of economic reasons for that. Gary's had a bunch of talks on it. He had the chart in his earlier talk. Campaign ended up being the same kind of thing. You can scale disk to get bandwidth versus tape, but like I said, we tried to build the POSIX thing out of this. We tried to build a big GPFS across cheap crap, and it didn't work. Not to say that consumer drives are all bad, because we're also still using them, but using them in a system that's expected to be built across something that's resilient is pretty tough. So we ended up building MarFS. Tell me if at any point if you guys just want me to skip over the MarFS part. Have you all heard the story in general across the system? Nods, no nods. No, okay, so I'll just go through it anyway. Okay, so I'm going to go over it just to make sure that we're all on a level set before I dive into the deeper things. So we could have built a campaign storage. A long-term storage system on disk is not something that's not a new concept. Doing it as cheaply as possible with cheap consumer drives that have higher bit error rates, have timeouts that may be far beyond what a normal RAID controller can handle, things like that. You can either build it expensive or you can build it unsafe. And those aren't really good trade-offs. We tend to move data in a way that even large parallel file systems, doing end-to-end writing, even if you're doing it correctly, there's a lot of implied locking and things to make sure that your data is intact and it's serialized properly down to the disks and all that. So we want to try to get away with all those things. So what we built was called MarFS. There's a C of data. C in Spanish is Mar, so MarFS. This is what we use for campaign. The big thing that we compromised on to make sure that we could maintain the performance of the system that we wanted and also not have to build a whole big complicated and rebuild a parallel file system. We didn't want to do that. What we wanted to do was build something that was as simple as possible that would get us what we needed. And what we needed was a big storage system that could have a lot of retention time and we could build it cheaply. So we compromised on update in place. You can't open a file, seek, and write. Not implemented. That's really the gist of it. That's what we compromised on, because what it lets you do, initially we were trying to leverage the cloud storage market, doing object storage. So we built this kind of around the idea of doing, you write something into the system, you're creating a bunch of objects, you're throwing them out into the storage system, and it handles it, because cloud is awesome, right? Everyone loves cloud. And it protects your data and it's erasured, and it turns out that that works for certain things, but when your data set is a petabyte plus, there are trade-offs there that don't really work for us. I'll go a little bit more into that in a second, but the things we gain by not doing update in place, though, we can do I/O shaping at the ingest. So this isn't really a real file system in terms of it's a POSIX file system. It's real in that you can store things into it, get things out, you can manipulate your metadata the way that you normally would. But one of the things we knew is a priori moving data into the system, we know the shape of it. We're discovering it as we go. We're ingesting things. It's not, create a file right into it, create a file right into it. It's okay, well, there's 10,000 files I need to move. Let's do this the most optimal way possible by shaping that I/O, packing small files together, taking big things and chunking it up, and spitting it in there in the best way possible. So we gain a lot of IOPS on write that we save. And we can also, protect our I/O a little bit better too, because this isn't meant to be an online nearline file system you run your apps out of that write little tiny things all over the place, and you have to consolidate those and log them and all that stuff. It's meant to be as simple as possible, like I said. And my story for this was probably a little different, given even 12 months ago or even 6 months ago. I would have said something different about our goals. We kind of stumbled into these things through the follies over the years where we, tried to build things that were out on the edge and were interesting and cool. One of the things that at least I learned was that simplicity is absolutely key and transparency is absolutely key. So the things that you're storing into the system are pretty critical. What matters most is being able to go, even if it's not the most optimal way to do some things, if you can store it in a way that is super easy for an administrator to go in, because I have a foot in both camps. I'm an administrator, I run the systems, and I help design them, so I get to eat my own food when I make it. And if I burn the cake, it's bad. So as these things happen, I mean, nothing's perfect, right? You're going to have problems in your code. You're going to have problems with hardware. You're going to have problems with networking. I mean, something will go wrong. And what we've learned over the past, couple of years of running this in production, I mean, our initial stab at this, I say we were conservative. We built a 30 petabyte system out of it, going to 60 petabytes now. And being able to go in after the fact, after you know something went wrong, or after you've discovered something went wrong because of the protections you put in place, and trying to figure out what went wrong and how to avoid it going forward has been absolutely key in us saving users' data over the past couple of years. Because obviously we have bugs. It's software. If you say the software has no bugs, it's not software anymore. It doesn't exist. So we've been a huge focus on when we built it. I mean, I didn't realize what we were doing at the time. It was making a system so easy that we run a 60 petabyte system with half of a person. And I can sleep nicely at night because at the end of the day, I know if something goes wrong tomorrow, I can probably recover whatever it was. So MarFS has a couple things that compose the MarFS software component, and it's a fuse daemon. It's not really meant to be super performant, it's meant to be okay performant. This is really just a view for users, humans, to get in and mess with metadata, change permissions, update files, or not update files, update file names and metadata, and to read with naive apps that don't know how to read into our API. So you can use Vim, you can use whatever, as long as you point it at a temporary thing over there, or open it read-only. There's a library that contains all of the functions you need to call into. There's a data abstraction layer and a metadata abstraction layer that have, I should have counted them up, but 20 calls or something you have to implement to make this whole system work. So if you wanted to plug in a different metadata or data repository, there's a very small set of things you need to be able to support, get stream, put stream, the metadata POSIX ops kind of thing. PF tool, which Gary talked about briefly in his talk, that's the load balanced parallel movement tool, and then some admin utilities to make my life not suck. One of the other things is we didn't want to have any serialization points in the file system as much as we could. And anyone who's seen any presentation of MarFS has seen this kind of okay diagram before. But we wanted to be able to dial up and down every single part of the system, whether it be bandwidth or metadata ops within a tree or metadata ops within a directory. And within a directory, sharding is not something we've actually implemented yet. We've done some testing and some stunts, but essentially we tried to make sure that whenever you need to dial the system in, you want to build it as cheap as possible to do your workload. We can dial in that exactly to what we want to do or what anybody else wants to do. If you only need to do a small number of metadata IOPS per second, or you only need to do create rates at some low rate, build that. It's cheap, right? Or if you need to go a trillion files in a directory or a trillion files in your tree and you want to be able to scan them quickly, that's something that you can build out as well. It's just a whole bunch of metadata servers that you shard across. So speaking of stunts, I presented this a couple years ago at a lightning talk at PDSW at supercomputing. But we did a stunt on Cielo, our outgoing system in the secure, as a test to see how fast can we go if we take the idea of that chart and build it out onto a big Cray supercomputer that has a really fast interconnect and a whole bunch of DRAM that we can pretend is a storage device. And we got to almost a trillion files. I was so disappointed by this. 968 billion files isn't a trillion. And I also didn't get a billion file creates per second either, but I really wanted to, and I got so close, and eventually what happened was I knocked over the network and all the admins said, well, we're not reviving this damn system again because it's 9,000 nodes and it's fragile because it's a Cray. Not to say that Crays are fragile. I don't want to make anybody angry. But it takes a long time to get the thing going again if somebody knocks it over. And this was pretty rough on the network. It was not designed to do a full fat. Every single node can talk to every other node, and I had a queue depth of 1. So every file creation on the system was a transmittance across the network and back per file. We didn't do any queuing. We didn't do any batch stuff, right? This was just everything in flight. And I think it was a 5D torus. Gary, do you remember? 5D torus, which is not designed to do an all-to-all, essentially. I mean, it's designed to do all-to-all for MPI purposes for doing collectives, but not necessarily hammering the network in every direction possible at the same time for 10 minutes, which as long as I could run the damn thing. And the same kind of thing on one of our smaller systems, the Open, before we retired it. We're trying to make sure read go as fast as possible as well, just for ripping through a system. I mean, if you put a trillion files in a directory, you better be able to read through it as fast as possible. So we did a sharded read there. And we had something like a 400x speed up. And this is not a new or fresh system or anything like that. It was an older AMD, I think it was Magny-Core's architecture. So it's fairly old. But that was fun to build, and it was interesting, and it showed that the design itself is not inherently limiting, at least. I am behind. So here's what a file looks like in MarFS. This is a multi-file. Multi in this context is a large file that we have chopped up into increments that are manageable for whatever the underlying subsystem is. So in this case, or in our production case, originally it was a gigabyte-sized chunk. So a petabyte-sized file becomes 1 million objects. That said, 1 million objects sounds bad, but when you can do them all in parallel, you can get some good performance out of that, because one of the things we need to do is move this as fast as possible up and down through these tiers. So MarFS itself is, at the top there is your metadata file system. In our case, we're using GPFS. That's not implying that you have to use GPFS by any means. You just need something that supports holes in files and extended attributes, and you can implement that in other ways. Extended attributes is just our POSIX interface. You could do it with key value stores if you really wanted to. Like I said, you just have to fill out that MDAO. But at each level of the tree, you've got a regular directory tree, and then each file has extended attributes that tell you, or tell the MarFS system where that data is stored, so which object system it happens to be, how many objects there are, how big they are, all that kind of thing. There's a lot of recoverability embedded into the objects themselves as we write them. So all of that stuff that's in the X headers there and the original path that even the file was written on and creation time and things like that are embedded within every object. So on a petabyte-sized file, even if you lost all of them except for one object, you at least know what you lost. Even if the metadata system falls over and the only thing you find out of that 1 million objects is one of them.
Need to be distributed. So the underlying the file system that supports the metadata. The example is GPFS.
Yes.
Does it need to be distributed?
It does need to be globally visible.
Globally visible.
Yes. So by whatever means you do that, it doesn't necessarily have to be globally visible, because it doesn't have to be a parallel file system. Right. But if you had, say, an NFS namespace and you have found a way to map X headers to embed it properly, you could do it with something like NFS. It doesn't have to be a parallel file system, but it does need to be globally visible. I should have said that as well. And so the other end of the spectrum, what if you have a whole bunch of really small crap that you want to pack together and put into this file system? You don't want to be objecting your object store, whatever the storage system is at the bottom end, which we've already said is cheap, crappy disks or unagile things. You want to be able to take those 1 million files and put them into something that maybe gives you 10 IOPS or 10 stores rather than 1 million. Object stores were not really designed for 1 million IOPS. If somebody comes up with one that can actually do real protection, things like that might be different. But in general, we found that if you put a parallel workload that's across a bunch of hosts onto an object system, and you're intending to go something like 5 to 10 gigabytes per second per client, you're not going to do it doing 10K puts and stuff like that. So MarFS takes those and packs them up to whatever the object size you specified is, and just lays out a bunch of files within an object as it stores them. And again, that's completely handled by a single client. There's no serialization points anywhere in this as much as we can do it. It's as async as possible. So the only thing that's really synchronous is that metadata stuff at the top. So like I said, we originally started out with a commodity object storage system. And this is one of the things that we realized going in, that a lot of them are very black boxy. They all kind of sit on file systems themselves, but they have their own data formats. And an administrator can't go in and figure out what happened, a week or two ago when they look at an object that's corrupted or something, didn't get stored, or you've got some of the parts, but the other parts didn't land, that kind of thing. So what we ended up doing was developing our own object storage layer. I say object in quotes because it's really just a bunch of file systems at the bottom. But the interface that we expose via the MarFS API for that is very object-ish in terms of put stream, get streams kind of operation. So you're not an IOP-driven workload by any means. And it also gave us the ability to do multi-tiers of erasure, which I used to think was a really cool thing, and it used to be the thing I'd harp on about a lot in building this. And maybe that's still novel, But you can do this in other storage systems these days. This is 3 years ago when we were designing this, so it was novel at the time, I believe. But what we do is you take the files coming in at the top of the file transfer agent there and spread it out across, say 12 servers in this case, with 2 chunks of parity and 10 chunks of data. And then at the bottom, we're still erasing that again to make sure that local disk rebuilds are all handled within a server. We're not traversing the network every time a disk dies, because that's the other hallmark of object storage systems is everything else is everywhere else. And you've got, even if you have a 10+2 across your object store or 20+4 or whatever it may be, you don't want to hit the network every single time a disk dies, because disks die a lot. And if all you're doing is shuffling data left and right across the network constantly to rebuild, that's a lot of wasted network bandwidth you could be using for serving I/O. So the bottom level keeps us local for most of the problems. And if we really lost a whole rack or something, then we start engaging the east-west traffic. And like I said, recoverability was key here. So when we're building the bottom end of this, the file format that we decided to do was, some people might say paranoid, especially if you're listening to the persistent memory talks that are all this, well, file system people are paranoid. We are, for a reason. Every stripes of these are stripes in a file that is laid out across these Z pools. These are 1 megabyte stripes, and we aggregate a bunch of those together into a file, so we're not creating a whole bunch of small stuff at the bottom level. And there's a CRC for every megabyte across, and there's also a CRC across the whole block, or the whole file that we write down. So you've got a way to, on a 1 megabyte granularity across these servers to figure out if you have a hole somewhere, which has saved our butts a couple times. When we found out that we were missing we were calling sync and we didn't look at the return code. Good job, us. But we were able to go through and read through all that data and find out where all the holes were and just rebuild them, at a very small granularity, which is super nice. And it's also very easy to read through these files and see what's going on. Even the storage paths are designed to be as simple as possible, so an admin can go and look at a namespace and go, okay, yeah, well, I know that the file would go over there in that format. And the only thing that's kind of tough is the scatter directories you put in for keeping all the files out of a single directory. So you have to do some hashing. But it's pretty straightforward. At the very end of every object, we also write a manifest that tells you everything that you wrote into there. All that create time attributes I was talking about earlier, those get jammed into the bottom of this. So you have actually 12 copies of that. So even if you only had one of this and you had no idea what was really in there, at the file system level, the manifest at the end of there tells you what you lost, if you lost anything. So what we learned at this point was, or so far, is that transparency at the lower levels of storage is key. I sleep well at night with this system running. I'm 1,000 miles away from it, and I'm not worried that it's fallen over because there's so much redundancy and so much transparency that even if something happened 3 weeks ago or 6 months ago, I can suss out what actually happened because it's just a bunch of files at the bottom and a bunch of X adders that tell you what it should have been. All of this has been key to us keeping the system running with the minimum amount of people. And it lets us use at the bottom level. So I've got that cool picture there. And those are all shingle drives at the bottom, Seagate standard archive drives, which are a pain to write to, but you can shape your workload. You can get, a quarter to a third of the bandwidth out of them. And for us, that's not the end of the world because they're so damn cheap. So we just buy a whole bunch of them, we get a bunch of capacity, and we get some bandwidth for free. And as long as you treat them nicely, they aren't the worst thing in the world. But yeah, as I said, it's simple. So ongoing work right now, we're working on building an RDMA native transport. We're hoping to deploy that in the next few months. Right now we're just using NFS for the data access at the bottom level, which sounds pretty icky, and it is. We're creating a fuzzy data abstraction layer. I call it fuzzy because it's a fuzzing layer that will return random garbage back to the thing that's calling the API, so we can test our top-level software like PF-Tool or the Fuse daemon, that kind of thing. We have some pretty fine-grained I/O timing that we've been adding into the data abstraction layer and metadata abstraction layers to find out where our bottlenecks are if we have a performance problem. We also have a modification or hashing algorithm that lets us do live migration at the bottom level. So as we've created these pools that are fairly big, we can throw out another quarter of the system, 15 or 30 petabytes or something like that. And if the old disks were dying and the new disks needed to be there, we could do that live now. And something even more cool. So we built MarFS, we've got scalable namespaces, we can do quotas pretty easily, it's easy to understand and administer, has optimized write I/O characteristics, it sounds an awful lot like something you'd want to build an archive out of. So that's what we're going to do. That's what Marchive is. It's a simple extension, simple, right? You're taking those ZFS pools at the bottom, you're replacing with something that handles tape. I mean, it could be LTFS, it could be whatever. We're going to probably use heavily just because we're familiar with it and we have a lot of local expertise, but you could just do whatever at the bottom. And really the only thing we're losing is agilely reading from Fuse. We'd have to turn off data read, because obviously you don't want to have users doing a grep and having it mount every tape like every HSM in the world has done in the past 30 years. And you want to batch process for ingest and recall so you can optimize your ordering when you're recalling data. All of that's kind of built in if you're doing something that already handles tape generally well as a storage backend. So all I'm talking about here is automating this, building the tools that let you move data in and out, and making users understand that this thing over here is really cold, frozen. I mean, you can't do things nicely to it. You have to say, this is what I want to get back, and we'll put it somewhere nice for you. But that's all there is. I mean, you leave the disk layer there to do I/O shaping, but you can do erasure across tape with this, which is pretty hard to do in parallel generally. So you could have 100 tape drives, and you could write to them in stream, and the only overhead you'd have is generating the parity. So you'd lose 10 drives to parity or something like that. But that's a hell of a lot better than just striping 8 wide and hoping for the best, or replicating. So I've talked about layers of storage through this, and it's by design, like I said. Users don't typically think about where they put their data until you say, go delete it or go find it again. They have bad memories. I mean, granted, the things they wrote last week they remember, but the things they wrote 3 months ago, maybe not. So in a user-driven system, we've got so many extra tiers. How do we expect users to be able to keep track of that? Short answer now is we expect them to keep track of it, and that's not a very great way to run forward. But what we're moving towards is giving users a view of that metadata across every single tier to be able to find where they stored their crap and move it to where it needs to be, or delete it if they don't need it anymore. So that's GUFI, the Grand Unified File Index. This is a kind of extension of the way we design MarFS. Is we try to pick up all these technologies and things that have been built over the years that are simple and easy, and everyone understands them, and they've got open source communities that back them, and take those parts and jam them together in a way with a little bit of glue that makes it useful for us. So this is not as simple as just flattening a namespace and doing queries, right? Because there's been products that have done that for years. If you want users to be able to access something, you can't just flatten the namespace and hope you're going to get performance out of it, because you end up querying the whole damn thing every time a user comes in. You get to do the access down through the tree to make sure they've got access to that file, even though they own it, they might not be able to access it, kind of stuff. So this is just trying to leverage existing tech as much as possible and build something that just screams in terms of metadata performance for reads, for users saying, find me that file I wrote 6 months ago or 3 months ago or yesterday if they have bad memories, and tell me where it is, tell me the attributes of it, and tell me how I can move it somewhere more safe or get rid of it. And again, this is designed to be as simple as possible so that it doesn't really matter if it's got the wrong answer sometimes, but I mean, it's obviously not going to, but we wanted to keep it simple so that the administrators for the system can just let it run, and updating it is fairly straightforward, that kind of thing as well. And I think my laptop is locked up. That's awesome. Okay, maybe not. Sorry. Awesome. Hang on a second. I guess I'm going to hotspot and get this thing back going.
You need a nickel to put it in the side slot there.
Do you have any? It's like doing a live demo, except not. Come on. There we go. Look at that recovery. Thank you, Chrome. Okay. So moving into this, like I said, we didn't want a flat namespace because it's great, but every time you have to update anything very high in the tree, say some admin decided they didn't want it being called /luster/ my project name, I wanted to change that. Flat namespaces mean you have to go and clean up all that. So if you've gone from /luster/ project A to /luster/ project B, normally that's just a rename, and that's fine. But if you have a flat namespace, you have to go through and rename all the other crap below it, which could be a trillion files. And we really don't want to do that if we don't have to. And security becomes a nightmare for things like that as well. As you have to actually go through and stab at the database or whatever you're doing at the flat namespace to make sure that the user, even though they own it, they don't. I mean, you have to follow POSIX for this. They can't just stab willy-nilly at it. So, like I said, we're trying to leverage all the things that already work well in namespaces. So we've got POSIX permissions. We can do tree walks. We want to make it go as fast as possible, so it's breadth first search for parallelization. And I'm just going to show a picture because it's easier. What GUFI is, and at its core, is a bunch of, we replicate the directory namespace in a GUFI namespace. So whatever your source file system or whatever it may be, we replicate the hierarchy in GUFI. And then at every level of the tree, we're taking, a trillion files or a million files or 10,000 files or 5, whatever it may be, and jamming it into a little SQL database in every single leaf of the tree. So if you have files, instead of doing a read dir stat to read everything, you're opening up a small little database and just ripping through records as fast as you can. But because it's so parallel, it's placed across the tree, you can fire off threads and just let them walk down as best they can and pick up information. And there's summaries of things in the tree as well in databases. But one of the cool things here is that if user only, maybe other sites are different, but at least at our site, users might own 5% of a file system at best. So when they fire off a query and you've gotten a flattened namespace, you end up reading a hell of a lot more you need to. And in this case, they just go, okay, well, you don't have access over to those things over there, so the 5% of the file system you need to scan is focused on. The user gets an answer back pretty damn quickly. But an administrator can still rip through and look at everything as well.
The keys are the full paths? The keys are the full paths?
The keys are the file names.
The full path.
No, just the file names.
Just the file.
Right, because if you put the full path in there, you're down the same route that you've gone before with the flattened namespace, and that rename becomes nasty. And at rename for high in the tree on this is you rename system A, blah, 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 over to system B, blah, 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 and the whole thing just moves with it, because all it is a rename. You don't have to go through and reconcile. And one of the things that we really wanted to focus on for this was being able to actually keep this relatively up to date. Granted, users, you can expect them to remember the things they put into the system in the last couple of days, generally. But what we wanted to be able to do is roll up the GUFI index as fast as possible. So we're working on ripping metadata out of Lustre in an efficient way and doing incremental updates as easily as possible, so that when 5% of the tree changes, all you're doing is 5% of the work that you did when you initially created the index. So you have a trillion files in here. You really don't want to be updating that every day or 2 or 5. Even if you do make it fast, it'd be really nice to just update the little parts that changed. So we're working on that for Lustre, we're working on that for GPFS, we're looking at a MarFS type of thing to rip it out of there, HPSS as well, so that you can keep a relatively intact version of what the users thinks they have everywhere and be able to go find their files. And it might not be up to the date within the minute or whatever. Synchronous for that is crazy, because then you have to build an indexing system that can run at the speed of whatever you're trying to index, which seems pretty rough. But every day kind of thing. If it takes an hour or so to update the thing every day, let it run. And we don't want to tickle the real file systems in a way that's going to knock them over either. You could brute force this by just doing parallel tree walks and statting literally everything and say, okay, well, what's different? But it's not a very efficient way to do it, and everyone will hate you while you're running your indexing tool if you have to tree walk every single time. So there's just a couple of quick slides on what we've got into the various databases. I'm not going to really focus on these because you can download the slides. It's also on GitHub, so you can just go grab it and look. But basically all the things that you might want to query over are contained within these databases at the various leaves of the tree. So you've got things like size and average time of things below me and number of files below me. Basically anything you can think of that we as admins would want to query over, or as users, you can query over that. So files like with a name of blah, or contains blah, or creation date or update time within a certain range, that kind of thing. So I've got these in here. The formatting's messed up too, but there's a whole bunch of stuff, and it's open. It's pretty easy to add more if you want to. It's just changing the way you rip metadata out of the source file systems. But we try to be pretty extensive here in what we contained. So what's in flight now? There's a whole bunch of things that are in flight, but obviously if you're going to be querying this tree, you have to have some way to walk through it. So we've got programs to do that. There's a Fuse interface in progress that lets you expose the result of a query as a Fuse interface, so that users can just say, go find me these things, and they can go grep through them if they really wanted to, because all you have to do is point it back at the real system, assuming it's online. And as like I said, we're trying to work on Lustre, GPFS, HPSS, and a couple other sporadic file systems to be able to rip in updates and update them over time, so that at least you've got a relatively recent view of the file systems. And Gary talked about this real quick, but on his little dual core, that MacBook right there, he was running some initial benchmarks of GUFI, and I don't know about you, but almost 2 million files a second querying out of a little dual core hyper-threaded laptop from 2014 seems pretty good to me. And we're in progress of building a terabyte-sized DRAM machine with a whole bunch of threads at it to see how fast we can really make this thing go. But access is one of the most optimized calls in the POSIX in POSIX namespaces in Linux. So we're doing that an awful lot. Go ahead. What license? Good question. BSD. So these are all on GitHub. MarFS, PFTool, GUFI. Archive doesn't really have any code to it yet because, like I said, it's a lot of orchestration details, not necessarily a lot of coding. But they're up on GitHub, and you can go play with them. And we'll be adding more as we go, and we're continually improving the performance and resilience of the system daily because we have 60 petabytes of stuff sitting out there that we have to keep running. And as we learn, we inject it into the master. Good.
Why do you use multiple Z pools for storage?
Multiple Z pools of storage mode? Good question. I've been asked that before, and the easy answer is, so typically when you're building Z pools, right, what you're doing is building a VDEV of some RAID Z3 or something like that, or mirroring or whatever, and you create multiple VDEVs and put them all together in a single pool, right? That's where you're coming from. Right. The reason we don't do that is exactly this picture here. You can lose one pool in this case, and rather than rebuilding everything on that storage node. I mean, we're talking about nodes that are hosting 2 petabytes of storage. I really don't want to go read 11 petabytes of its neighbors to rebuild a petabyte of stuff. So the blast radius of this is a single pool going away is just reading whatever it contained times 10 or 11 for our striping scenario.
So when you lose a single pool, do you have to rebuild it? Do you have to read other stuff from the same node, or enough?
No, so that highlight there is actually the data placement across these servers. So you end up, if you blew out zpool 2 on storage node, whatever, the third column or something, what you end up doing is reading all the other guys in that stripe across horizontally and rebuilding all the objects that were on that pool before.
And that diagram, all the rows are striped?
Yes. Yes, and when we place things, we always pick a stripe that's across the middle. So we constrained our failure domains. There's not a random placement of objects across these. It's hashed, and then you pick a stripe that runs across a set of servers. What we're trying to avoid there is, I mean, we're talking about petabyte-sized files that have 1 million objects in them. If you place those completely randomly, this is the folly of object storage systems until they started to add in failure domain stuff. If you don't constrain the placement domain, your chances, if you have a 20+5, for example, and you pull out 5 disks, you've probably lost an object if you have enough objects, if it's placed randomly and uniformly across the system. What we wanted to avoid was exactly that, right? We can lose a lot of drives across the system, and you don't have to worry about blowout on a single object.
What vendor doesn't guarantee that you can lose 5 disks if they call it a 20+5 array?
20+4.
Oh, +4.
Yeah, so we want, protection +1 disks have been destroyed. Simultaneously, the power blipped and all your drives came back up, and oh shit, a bunch of them are missing.
Yeah.
So we wanted to avoid exactly that scenario because we've been there.
You talked about using open source as much as possible. Are you using Lucene for search or Solar? Or?
These are MySQL databases at the bottom, or SQLite databases at the bottom.
Okay.
Yeah. So.
And you're only indexing the metadata, right?
Correct.
A lot of this is scientific data. Have you ever thought about doing some really simple indexing, like min, max, average?
That's already in there as well. So as we scan, we keep tallies that are driven from the bottom up. They're optional, but if you enable them, you've got sums of average file size below me and things like that you can add in there.
Okay.
So yeah, they're there. So to narrow down your search as fast as possible.
So you were showing a diagram where you had chunks on disk that were about a megabyte.
Yes.
Setting that to this one. So those CRC32s protecting megabytes per
A CRC32, yeah. So yes, it's not necessarily protecting it, right? That's just us recognizing that something has changed. We're only looking at that as a verification that what we stored is what we thought we stored. It's not recovery or anything like that, right?
Right, but CRC32 is very big for megabytes. There's plenty of it.
Well, so I don't disagree.
Try to give a little bit of 2 sides of the conversation, otherwise you're just talking about.
Oh, sorry. So the question is why CRC32 over a megabyte is not very strong. It's what seemed to work at the time, right? We were looking for some basic verification that the data we wrote was correct, not necessarily catching every single bit flip. they could obviously be extended to something larger. There's not really anything stopping us from doing that. We have additional protections at the bottom level from ZFS as well. So really this CRC was just, did the bits get across the network and all the network checksums worked, but maybe we corrupted it on the way in, something like that. Make sure we've got that.
So it's a short-term CRC, it's not stored long-term?
No, it is stored. This goes down on the disk as well. So that's what actually helped us find when our protocol was working fine in the network, but our actual implementation details at the top weren't quite right. If we were extending this out to tape, you could obviously switch out that CRC. Right now it's IEEE 32. You could crank it out to some other 64.
To do that, and the data might have been lost.
What do you mean?
If you use the CRC equality to infer that the data is intact,
Mm-hmm.
and then you recompute it and send it out the disk, and that first decision was wrong,
You could.
that data is good, right?
Well, it's good, but the CRCs for the block. So, like I said, there's a 1 megabit level CRC as we go, and then a CRC for the entire 100 megs or whatever it is in a file as well. And I think the collision domain for that's fairly narrow. But I mean, that's just choice of CRC, right? I mean,
CRC 32 for a meg sounds weak, but maybe it's good enough for what you need.
yeah, and it's pluggable. I mean, you can change it. If you want to do SHA-256, you could, or MD5, or whatever you wanted to do. It's just a compute at that point, right?
But you're not using that for dedupe or anything?
No, absolutely not. That's no.
Error detection?
No, we'd have SHA-5 12 or something like that. But we'd doing global dedupe on something like this, or any kind of dedupe on a
Well, it's
petabyte scale
data,
system.
So the chances of it matching are pretty low.
Right, and the costs for doing it are so high in terms of serialization that no, thank
Well,
you.
your placement algorithm, because you're deduping it someplace you didn't want it.
Right, and then oops, I lost that one little dedupe chunk. Oh, it was 1,000 wide. Crap, I just blew out 1,000 files because they happen to share the same header somewhere. I mean, no, thank you.
On your Z-pole picture,
Yep.
maybe I'm just being dense, but I can't understand your redundancy level.
Okay.
How much actual extra capacity are you guys, like for every terabyte?
So I think it comes out to about 30% total. So at the top, we're doing a 10+2. That's just libISAL from Intel. That's pluggable, obviously, for obvious reasons. And then at the bottom, the Z pools, these are 17+3 RAID Z3s. So they're not terribly high overhead. We end up writing little tiny chunks, which is why I've tried to aggregate as much as possible at the top. So it's a 10+2 over 17+3, which I think we worked out the math, and it was equivalent to doing a flat 170 plus 70. Plus 70 re-erasure is pretty damn hard to calculate unless you really want to make Intel happy or AMD. So yeah, it's pretty wide, and we can tolerate an awful lot of. If you do a correlated in time failure event that is not spatially correlated across a system like this, say you pull out 100 random disks, the likelihood of hitting enough in a stripe, there's only 240 disks in a single stripe. The likelihood of hitting a whole bunch in that one failure domain is fairly low. I mean, it has survived pretty catastrophic failures, firmware bugs, brownouts, all sorts of interesting things like that. We've ridden through all of that, and we have yet to actually lose anything because of a disk failure. Programming failures for sure, but that happens.
So going back to GUFI, at what point do you actually update the sequence? I mean, when do you actually update that SQLite database?
So updating the SQLite databases are done at whatever interval the admin decides to run it at, right? So what we're doing is we don't actually update them, right? We blow them away and recreate them. It's a hell of a lot easier just to keep things in reader order, and whenever a directory gets updated on the source file system, blow away that directory SQLite database on the GUFI file system, just recreate it, because it's faster to do that than it is to do a merge. Does that answer?
The deploy is only good as the last update.
Absolutely, yes. No, keeping it synchronous would have been a nightmare. I mean, we'd have to build an indexing system that can run at the speed of every parallel file system and every other storage system at LANL. And I think in every environment, that's probably a pretty tall order. And it breaks the design. If a user can't remember where they put a file 5 minutes ago or yesterday, how do you expect them to be able to shepherd their data?
So, follow-up question. Do you walk the entire file tree to reveal the index and to reveal all this minimum, maximum size information?
So you don't have to, right? And all you have to do is, sorry, so that question was how do you update all of these summaries within the GUFI tree as you're injecting a new entry? So there are certainly things that have to trickle up. right? If you update a tree and it's down at the bottom and, well, they're all named the same thing in this picture, so it's hard to say, but say at the bottom of the tree there, they trickle upward as you update that. So if you scan the source file system and found that at the very bottom of the tree you had an update that put in a gargantuan file or even just updated it all that propagates upward through the tree. So you...
At every directory level, there's an SQL database for the directory as well as the files. The directory has a summation of everything in it and everything below it. So if nothing changed below you, you can just go and get it in one place. And so it's really, really efficient to, you only figure out what parts of the tree changed and all of those.
Yeah.
It ends up being way sub-second for a huge tree.
Yeah, so what Gary was just saying for the camera is that all these summaries are at a database at a tree level, and as you update a particular directory, the only thing you have to do is trickle those changes upward through the other summary directories. So it's pretty efficient to do that. So it's a minimal change set, minimal change set between updating something in the source file system and updating something in GUFI. It trickles upward a little bit, but it's a bunch of small little databases that might be a megabyte at most. Any other questions? Happy to go into detail on any of this stuff. This is my bread and butter. All right, thank you.